we had a picture of a function. Here it is, y equals f of x. And the idea was that we wanted to describe the slope of a tangent line, a line that is tangent to our curve at a particular x value, and we call that x value a. So this is our slope of a tangent line at x is equal to a. And the reason that we actually cared about that slope is that the slope of that purple line, of that tangent line, told us the instantaneous rate of change of our function. In other words, it told us how steep this function is. Alright, so this was our goal, and the way that we set this up is that we chose a second point on our curve, and we called that x value just plain x. It gave us a point on the curve, and we drew a line, which is a secant line, between those 2 points. And so, if I'm looking at the secant line, and I want to find the slope of that secant line, what I need to do is I need to have 2 points. And the first point is the point a comma f of a. I get the y value by plugging a into my function. And my second point, my x value is x, and my y value is f of x. And so if I want to know the slope of this secant line, well, I'm going to take the difference in my y's over the difference in my x's, and so I would have something that looks like f of x minus f of a all over x minus a. And now that formula right here, just this portion of it is our slope of our secant line. And the cool thing, the thing that happened at the end of the class, the action that we saw last time was that when we take this point up here, the one that corresponds to the x value, and we allow that x value to get as close as possible to our value of a, well, this second point up here, the x comma f of x, gets really close to a comma f of a. And once they're just about on top of each other, then what we have is our tangent line. And so what we're really doing is that we're allowing x to approach a, and we're taking the limit as x approaches a of the slope of our secant line. So when I include the limit symbol along with the slope of our secant line, then that whole entire expression, that is our slope of the tangent line. And so our definition is that this is called our derivative. And so this is our derivative of f at x is equal to a. And the symbols that we use to write this down is we say that this is f prime of a. And this is our limit definition of a derivative at a point. Okay? And so this expression is telling us, if we can do some calculations with this expression, it tells us how steep our curve is right at the point x is equal to a. It tells us the slope of that tangent line. All right, so take a second and say hi to one of your neighbors. All right, and I'd like for whoever of the two of you is closer to this wall, please tell your neighbor this formula out loud. The derivative of f at a is equal to, and then say the formula. Go ahead and say it out loud. All right, stop. If you haven't finished it yet, then you've been taking way too long. Okay, so this is our limit definition of a derivative. And as far as material out of 2.1 that will be part of our exam, the only material out of 2.1 that you will be required to know for the exam is to be able to state this definition right here.
Written that way, or actually write word for word?
So you could write the derivative of f at x equal to a is equal to, and then these symbols right here. So f prime of a equals the limit as x approaches a of f of x minus f of a all over x minus a. Okay, so the rest of the material I'd like to talk about is definitely stuff that you will see, but you won't be tested on it until exam 2.
So we can just write that, or do we need to kind of describe it in words as well?
At this point, so on the review sheet that I gave you, I asked you to be able to describe it in words. We're going to hold off on that part
okay.
until exam 2.
Just write that.
Yes.